going to do is we're going to talk about this guy. This guy is called Pythagoras of Samos. Have we heard of Pythagoras of Samos before? Yes. Do you remember Pythagoras of Samos? No? Okay, Charlie says yes, Kulani says no, Emmanuel says yes. Okay, so some of us have heard of Pythagoras. Pythagoras, not of Samoa, of Samos. So there was a place in ancient Greek called Samos, not Samoa. He wasn't like the rock Samoan. No, not that kind of Samoa. Okay, he's Pythagoras of Samos. Okay, and he came up with the Pythagorean theorem, and we know the Pythagorean theorem. We've done it at school, right? We know a squared plus b squared is equal to c squared. We've all done that before, right? Yes, his name was Pythagoras. Yes, absolutely. That was his name. Now, here's the nice thing. Here's a fun fact about Pythagoras. Now, Pythagoras of Samos was a mathematician and he was a philosopher. Right. He was a philosopher, but Pythagoras didn't actually come up with the Pythagorean theorem. He didn't come up with it. Okay, so Pythagoras was a very famous philosopher, much like, other famous philosophers like if you've heard of Plato or if you've heard of Socrates. Okay, I know. Emmanuel, if you're feeling nice, you could name your kid Pythagoras. I mean, it would be interesting. When you have a son or a daughter, you can name them Pythagoras. Let's see how that goes. Okay, so he was a philosopher and he had followers. And Pythagoras's followers were called Pythagoreans. They were named Pythagoreans. And his followers came up with the Pythagorean theorem and they named it after him. So he didn't actually, by the time the Pythagorean theorem came about, Pythagoras was already dead a couple years, and they named the theorem after him. Imagine being so famous, guys, that your followers named something they discovered after you. I feel like, oh, guys, like maybe I should become an influencer so that when I die, like my followers can like name something cool that they discover after me. It will be called the Teacher Coco. I like it. I like the sound of that. Yeah. And then they named it after him. Imagine, guys, I must be, oh, thank you. Thank you so much, Emmanuel. I'm honored. I'm honored. Thank you. Lovely. Thanks so much. All right. So we all know, I know, but it's also because I'm sweet like that. Maybe they named chocolate. Maybe chocolate was named after me. You never know, Narisha. You never know. All right. Okay. So we're going to do a little bit of Pythagoras just for us to get back into the groove of Pythagoras. I'm going to give you guys these 3 questions. We're only going to do questions 1, question 2, and question 3 of Pythagoras. Okay, and I'm going to show you guys the shortcut that we can use in order to use Pythagoras because we know how to use Pythagoras. By the way, we can only use Pythagoras when we have a specific kind of triangle. Who knows what kind of triangle we need in order to use Pythagoras? Yes, that's it. Absolutely, Emmanuel and Narisha. That's it, Princess. Well done. It needs to be a right-angled triangle. Otherwise, we cannot use the Pythagorean theorem. All right, I'm going to give you guys 3 minutes. This is not a difficult exercise. We're only doing questions 1, 2, and 3. Pop your favorite emoji in the chat. When you're ready, I'm going to fill up my water glass. I will be right back. Kulani already done, and there's still 2 minutes to go. Well done. One more minute, guys. Oh, Narisha, what a cute emoji. I love that. How adorable. Emmanuel, yours too. I love it. Nice one, Charlie. All right. Okay, guys, that's time. Okay, so remember, guys, this is Pythagoras. We've been doing Pythagoras since grade 7. So we're definitely going to take some shortcuts here because we're in big school now. So instead of us writing out a squared plus b squared equals c squared and Pythagoras, we're just going to take a quick shortcut. So I'm just going to go number 1. I'm automatically going to do this. X is equal to the square root of 9 squared plus 12 squared. But remember, Pythagoras is a theorem, so we must name the theorem. It's like a geometry theorem, so we must name that we've used Pythagoras. Therefore, x is equal to, we must do it, is equal to 15. All right, we must give credit where credit is due. We didn't make it up ourselves. If you make up your own theorem, then we can write the Narisha at the end. Okay. Okay, number 2, we're going to go x is equal to the square root of 10 squared plus 24 squared. And again, give props where they are due. Give props to Pythag. Therefore, x is equal to 26. Right. And for the last one, number 3, x is equal to the square root of 7 squared plus 3 squared. Again, we must pay homage to Pythag, and therefore x is equal to the square root of 58. I know that most of us feel like clicking the SD button. Please don't. This is called surd form, and this is the most accurate form that we get in mathematics. Much like when we have fractions, we do not change our fractions into decimals. We always leave them either as a fraction or we leave them in this underneath the square root. So don't click the SD button. Leave it as the square root of 58. This is the most accurate answer. Unfortunately, if you click SD, your calculator is cutting off the last bits of your calculation or your decimals. So you'll find that because it's a surd, it goes on forever and ever. Leave it as a fraction. I mean, as a surd, or leave it as a fraction. All right. Okay. If we've made a mistake, Narisha, I know it wasn't intentional. I mean, it's Pythagoras. We've done Pythagoras before. But today isn't actually about Pythagoras. Today is about trigonometry. And we're going to learn about the guy who actually discovered what is better known as the foundations of trigonometry today. And his name was Hipparchus of Nicaea. Now, he's the guy who actually discovered, using the Pythagorean theorem, what we now know today as trigonometry. Okay, so I'm gonna show you guys something. Let's take, for instance, that first example that we had. Or let me give another example. If I have a triangle, right? And this triangle has some angle over there, and it's a right angled triangle, right? If this is 3, that is 4, and that is 5. Let's call them meters, meters, meters. Now, what Hipparchus figured out was that if I have a triangle, and let's say, for instance, the angle over here is 40 degrees, right? And I have another triangle, a bigger triangle that is also right angled, and it's also 40 degrees. What do we call these two triangles? Who remembers? We learned about them in grade 9. What kind of triangles do we call those? Yes, that's it, Emmanuel. Good. I have 2 similar triangles, right? Excellent. I have 2 similar triangles. So Hipparchus discovered that if no, his name, Narisha, no, his name is not trigonometry. No, I know it would have been cool if it was, right? But it's not. Okay. Actually, yeah, that's a good question. That's a good question. Why is his name not trigonometry? We need to ask somebody. We must ask Mr. Maths. Ask your maths teachers, make it make sense, right? So he discovered that if each of the angles have the same, if we have the same triangle with the same angle over here, the ratio of this side of the triangle to this side of the triangle to that side of the triangle is going to be the same no matter how big my triangle is, right? Because if I have 40 degrees over there, this is going to be 50 degrees over there. This is also going to be 50 degrees. Both of them are going to be 50 degrees. And if this is double the triangle of the smaller one, this side is going to be 6 meters. This side over here will be 8 meters long, and this side would be 10 meters long. And Hipparchus figured out that every single triangle, no matter how small, even if our triangle was this small, as long as there was a 40-degree angle over here, the ratio of this triangle to that triangle to that triangle will be the same because of the angle over there. But now he was like, okay, that's great. That works for a 40-degree angle. Does it work for every other kind of triangle? And so Hipparchus went to work. He went to work. He started with a 1-degree triangle. He started with a 1-degree triangle, and sure enough, he figured out that if there's a measurement for this side, and there's a measurement for this side, and there's a measurement for this side, if the triangle is bigger, but the angle is still 1 degree, then the ratio holds. The ratio will be exactly the same. And then after 1 degree, he went to 2 degrees and he measured. Does the ratio hold on all sides? Yes, it does. And then he went to 3 degrees, did the same thing. 4 degrees, 5 degrees, 6 degrees. He went and he did all the degrees in a right-angled triangle, and he found, yes, indeed, every single one of those triangles has the same ratio based off of the angle that it has at the bottom of the triangle. And you're absolutely right, Emmanuel, the man had time, because back then, they didn't have fancy scientific calculators like we do. Lucky for us, we don't have to do that. We don't have to do that. We've got our calculator. Back then, they used to walk around holding a book full of all the different degrees of every right-angled triangle based off of Hipparchus's work, the ratio of each of the sides. They did. They walked around with a huge book that had every single angle, every single ratio. So yeah, they did that, right? But lucky for us, instead of us now having to use them in bits and pieces and pockets, he was like, all right, let's say, for instance, we have a triangle. We have a triangle, and we know that the angle over here is 25 degrees, and this is a 90-degree angle. Now, he said, let's say, for instance, I only want to compare this side. Let's say, for instance, this side was 7 meters. I want to compare that side is 7 meters, and I want to know what this side is. It's not necessary for me to figure out what this side is. I only need this side and that side, because as long as I've figured out what the angle or what the ratio for a 25-degree angle is, I can figure out what that side is going to be. I know the ratio of every triangle. Also, if I have, let's say, for instance, if they only give me this side, if they say this side is 5 meters, and I want to know this side, then I don't need the other side. I've got my angle and I've got this side, and I've got my book that tells me what the ratio of each of the sides is. I can figure out what my longest side is. And that's where the idea of sine, cos, and tan was born. That's where sine, cos, and tan come from. All right, so that is the the background of trigonometry. We are using angles and we are using sides because for every angle in a right angle triangle, there is already a predetermined ratio for each of those sides. And this guys is like revolutionary because Hipparchus of Nicaea helped us. I know, probably because they all had a book, so they could all walk around with a book and they didn't have to study that much. They could cheat. It was an open book test every day. All right, and this is the beauty of it. The Pythagorean theorem put together with the sine, cos, and tan that Hipparchus figured out has helped us build every single building that is standing today. Still is still built off of the Pythagorean theorem and off of sine, cos, and tan. Okay, which is just, guys, it's like magic. I don't know. It's so somehow Harry Potter has nothing on this because this was some beautiful work that they did back then. He is a legend. He is 100%. Him and the Pythagoreans, they did beautiful work, guys. And yeah, this is why we say, absolutely, yes, Emmanuel, if your theorem can actually be used to better society, you can patent it, like Mark Zuckerberg patented Facebook, like how Bill Gates patented Microsoft. You become a multimillionaire, a billionaire, if you will. So yes, absolutely. A lot of this stuff is very important. And your name gets shrouded in history. We write about you in history books. Wow, how nice. Hey, how nice. Okay. All right. So let's learn a little bit about this Pythagorean theorem or these trigonometric theorems. Okay, so we're going to learn an acronym called SOHCAHTOA. And if you are seeing this for the first time, I want you to take a screenshot of this thing that I've put in purple because it's going to come into play right now. We're going to be using it right now. Okay, I'll give everybody 5 seconds to take a screenshot for. Okay, excellent. All right, we're going to learn how to use these triangles to kind of label things ourselves, right? So I'm going to give you guys this triangle. It's a right-angled triangle. Okay, I'm going to say that this side is equal to 4 centimeters, this side is equal to 3 centimeters, and this side is equal to 5 centimeters. All right, so I'm going to give you guys an angle theta. Now, this angle is called theta, but we're only calling it theta because the symbol theta stands in place of angles. So whenever we see a triangle that has a theta, something that looks like this, it's a Greek letter, theta, or beta, or as the Americans say, beta. We don't call it beta in South Africa, we call it beta, and alpha. These three things stand in place of any angle that we want. Any angle, okay? Because thanks to Hipparchus, it doesn't matter what the angle is, we've already figured out the ratio that goes along with it. All right, so if we see that theta, tell me in the chat, guys, what does this theta actually stand for? Tell me in the chat, what does the theta stand for? Who remembers? It's good. It's an angle. Thank you, Kulani. It's written on the screen. It wasn't a trick question, I promise, guys. It's written right there on the screen. Whenever we see a theta or a beta or an alpha, it actually stands for an angle, right? So I'm going to name this one theta, and I'm going to name this one beta. Now I'm going to bring back that that acronym SOHCAHTOA. Okay. Now this SOHCAHTOA actually stands for those three things that Hipparchus figured out. Sine, that's S for sine, C for cos, and T for tan. And now if you look at your scientific calculator, I've got the unfortunate pleasure of having this black one because I borrowed my white one to one of my students, and I'm going to get it back from him after the holidays. Right, you will see on your calculator, there are actually 3 buttons that actually have sine, cos, tan on them. Can you guys give me a thumbs up if you come across that sine, cos, tan on your scientific calculator? Yeah? Do we all see it on our scientific calculators? Excellent. Good stuff. All right. So what this actually tells us is that in relation to the angle that we're looking at, sine of any angle will be the opposite side divided by the hypotenuse. That's what SOR stands for. SOR is opposite over hypotenuse. No. Okay. The reason we call it, I know it's written sin. Sin is short for sine because the actual name, Narisha, we actually spell it like this. We spell it like that. That's how it's spelled. Okay, so because it's too long for your calculator, they've just shortened it to sin. Okay, sin like wrath and pride. No, not that kind of thing. Okay, right. And then the cos over here, this C stands for cos. You can see the cos on your calculator, but it's not actually cos, it's actually cosine. It's actually named cosine. So you will hear other teachers actually say cosine. Okay. So cosine or cos, the A stands for adjacent over hypotenuse, right? And T stands for tan, but it's not actually tan, it's tangent. Okay, as we will learn in mathematics, a tangent is where two lines meet. The point where they meet is called a tangent. All right, and that's why we call it tan. Tan has something to do with this right-angled triangle over here. Okay, and tangent or tan is going to be opposite over divided by adjacent. Okay, but now we're going to then have to figure out what is opposite, what is hypotenuse, adjacent. Ma'am, what are you saying? We need to figure that part out first. So whenever we see a triangle that we've been given, the step number one, without fail grade 10s, is to label our triangle. I'm going to ask you guys one more time. Whenever we see a triangle that we've been given like this, what is step number one? Tell me in the chat. Thank you, Narisha. Beautiful. Absolutely. And Hulani, you are on point. You are on point that the angle will inform us. And the way the angle is going to inform us is if we label it. Okay, so we're going to label it. Here's what we're going to learn. If we're going to be asked a question based off of theta, we're going to do everything that we're doing inside this triangle in reference to theta. So here is theta. This side over here, the side next door, right? The side closest to theta is called our adjacent side. Right? The side always next to is called the adjacent side. The side furthest away from the angle theta is called the opposite side. This is the opposite side. And the longest side, we know this from Pythagoras even. The side across from the right angle triangle, this side is called the, thank you, Fulani, it's called the hypotenuse. All right, the hypotenuse. This is the opposite side. This is the adjacent side. And that is the hypotenuse. Okay, but I want us to be very careful. Hello, Bukosi. Welcome. Awesome to have you with us. All right, I want us to be very, very careful of something, right? If they ask us to write our ratios sine, cos, and tan in terms of the angle beta, then our labeling is completely going to change. Now, think about this is the side next door. In relation to beta, what is this side going to be? Is this going to be opposite? Is this still going to be the opposite side? No, what side is this side now going to be? What's it going to be called? The what side? The one right next to, that's it, princess. Absolutely. This is now the adjacent side. Okay. The adjacent side. And that side now is no longer the adjacent side. The side is now the opposite side. And yes, you're absolutely right, Fulani. the side across from the right angle triangle will always be our hypotenuse. Yes, absolutely. So Emmanuel, the one, if it's, okay, so the hypotenuse will always touch our angle, and the other side that touches our angle is the adjacent, the one that always touches. Okay, that's the adjacent. Okay, are we okay with that? Cool, excellent. Right, so guys, this is why I'm saying before we can do anything at all, step number one is to label, because if we label wrong, if we get this step wrong, then our ratios are going to be wrong. Let me explain. Okay, I'm going to remove all of this lovely stuff here. Okay, I'll rewrite that 3 centimeters just now, and the 5 centimeters. Sure, I've just erased everything. Okay, this is 4 centimeters, 3 centimeters, 5 centimeters. Right. Now, if I say to you guys that I want the sine of theta. Yes, the one furthest away, Vukosi, that's the opposite side. Okay, correct. Okay, now if I want the sine of theta, the ratio for the sine of theta is going to be dependent on the angle theta. Now I have to use theta as my reference. So I know that this side is my adjacent side. That side over there, the one furthest away, that is my opposite side. And the one always across from my right angle, that is my hypotenuse. Now, according to sine, sine is equal to opposite over hypotenuse. Now, the ratio for that, according to my triangle, absolutely, Tristan, the opposite side is 3 centimeters over the hypotenuse, which is 5. Okay, and I love how some of you guys have not written the centimeters part. It's not necessary sometimes to write the centimeters part, because remember, guys, this is a ratio. It's a ratio. If I decide to make my angle twice as big, and I change this side to 10 centimeters, all I'm going to do is I'm just going to multiply this by 2 and multiply that by 2. The whole thing is just a ratio. So if this is 3 over 5, that just tells me about the ratio. The centimeters part doesn't really matter. I can increase it, I can make it smaller. The ratio is going to be the same on every side. Am I making sense? That's why the centimeters part isn't really that important. Unless they ask for the unit, it's not really the part that we're worried about. What we're worried about is the ratio itself, okay? Now, what if I say to you guys that I want the tangent of beta? The tangent of beta. Now, remember, have I labeled according to beta over here? Have I labeled according to beta? No, I haven't. I've labeled according to theta, so I can't. I now have to remove all of these labels, and I now have to label according to beta. No, not in this case, Vukosi, not in this case, my darling. And I will explain why. All right, I'm going to explain why in just a little bit. Okay, in this case, we're just looking for the ratios. And the ratios have everything to do with the sides. The inverse, we're going to get to before we get to the end of the lesson. Okay, so don't stress about that just yet. Okay, you got me? Cool? All right, now, if I want to find the tan of beta, I now have to label according to beta. Now, this side over here, closest to beta, that is the adjacent side. That side over there, that is the, now I'm calling it the adjacent also. The side furthest away, that is the opposite side. And that side over there is going to be the hypotenuse. Thank you, Kulani. I caught myself midway. I caught myself. All right, cool. So now I know that tan actually uses owa or towa, which means I need the opposite divided by the adjacent. So tan is opposite over adjacent. The opposite side is 4 over the adjacent side, which is 3. And Tristan, you don't falter, my guy. Well done. All right. Can I just get a thumbs up? Is everybody okay with the way that ma'am is manipulating the theta, the beta, the sine, the cos, and the tan? Yes, are we all okay with how ma'am's done this? I don't want to leave anyone behind. I want to make sure everybody's with me here. Okay, now I want everybody to tell me, look at the drawing. Look at the drawing exactly the way it is. I'm going to remove all of my prompts here. I want you guys to tell me what the cos of theta is going to equal to. According to the drawing, tell me the ratio of cos theta. Remember, I'm using theta. So label in terms of theta. And then tell me what cos is. Cos is the part of it, and that is adjacent over hypotenuse. And Tristan, like clockwork, just killing it, my guy. Absolutely, Vukosi, that's it, 100%. Right, because I want cos of theta, I need to label according to theta. This is my adjacent side. That over there is my opposite side. It's cause of your headache. No, Narisha, no headaches here. It's the cause of my headache. You know what, Narisha, I think if you don't go into mathematics in any way, I really think you should go into writing English poetry, like comedic poetry, because you never fail, you never falter. Like your punchlines are always on point. On point. I love it. I think you've got a future as like a comedic English writer. I love it. You're there. You are there. I see you. Okay. Cos of theta is going to be adjacent, which is 4 over hypotenuse, which is 5. And everybody is doing just, wow, excellent work. Amazing stuff, guys. Excellent. All right. Here's your next challenge. I'm going to give you guys 5 minutes. Okay, here is our triangle. I'm going to name this part over here theta. I'm going to name this part over here beta. And I'm going to put a right angle triangle over here. I'm going to name my triangle X, Y, Z. And I want you guys to label or to give me the ratios of these 3. Now, I haven't given you any numbers. So I want you to give it to me in terms of the sides of the triangle. So this side over here, from X to Y, this side is going to be called side XY. From Y to Z, this side is going to be called YZ. And this side over here is going to be called XZ. So I want you to give me sine theta is equal to XY over XZ, something like that. That's what I want my answers to look like. You've got 5 minutes, guys. Take it away. Move that down a little bit so we've got a bit of space. All right, pop your favorite emoji in the chat when you're ready, peeps. Sure, Tristan, you're like a machine, dude. How are you guys already done? Oh my word. And I gave you guys 5 minutes. It's not even been 2. So I'm just like, yo, wow. Okay. All right, then let's give everybody else a chance to catch up. Jeez, guys. Sure. Thanks, Theo, for the poopy emoji. Give everybody else 1 more minute. All right, peeps, that's time. Okay, let's have a look. Okay, to make things a little bit easier, and I should have done this before. I'm very sorry, guys. I should have written SOHCAHTOA on the side for you so we can remember. All right, SOHCAHTOA is very, very, very helpful. Okay, let's start with sine of theta. Now, I know I'm going to get theta for the next three, sine of theta, and I'm going to get cos of theta, and I'm going to get tan of theta. So I'm going to be using theta as my reference angle. So I'm going to label in terms of theta. So this is going to be my adjacent side. This is going to be my opposite side, and the one across from the right angle is always my hypotenuse. So sine of theta, sine is opposite over hypotenuse. So the opposite is xz over xy, right? Cos of theta, cos is adjacent over hypotenuse, so that's yz over xy. And then tan of theta, that is opposite over adjacent. Opposite is xz over adjacent, which is yz. Right, 3 marks. 1, 2, 3. Okay, now let's look at sine of beta and cos of beta and tan of beta. Now, my reference angle has changed, which means all my labeling will change as well, right? Except for the hypotenuse. The hypotenuse is pretty much the same, right? So this now becomes the adjacent side. That side becomes the opposite side, and the side across from the right angle becomes the hypotenuse. Okay, then we can label. All right, sine of beta, sine is opposite over hypotenuse. Opposite is now yz over xy. Cos is adjacent, which is xz over hypotenuse, which is xy. And tan of beta is going to be opposite over adjacent. Opposite is yz over adjacent, which is over xz. Yes, correct. Yes. Okay. Tell me how much you got out of 6, and Emmanuel, you're absolutely correct. Sine and cos swap, which may have something, I don't know, it may have something to do with the fact that one of them is called sine and the other is called cosine. Maybe. Any familiarity there? Are we seeing? Sine and cosine? right? For those of you who got 5, are we okay with what? Are we okay with where we didn't quite get it? Narisha, stop. Beautiful. Well done, guys. If you got 5 out of 6, I hope we kind of sort of saw where we didn't quite get it. Okay. It's very important that we remember, guys, label, label, label. Labeling is always the important thing. Okay, that is always the most important thing. All right, so let's go ahead and look at the next thing. Now we've learned about the ratios, the different sides of a triangle. Now, I'm going to do this. I'm going to take this triangle over here, and I'm going to name it, I'm going to give it an angle theta. I'm going to name it A, B, C. I'm actually going to give it dimensions this time. Okay, I'm going to make this side equal to 5. I'm going to make this side equal to 10. And I'm quickly going to use Pythagoras to find the other side. 10 squared minus 5 squared equals 5 root 3. Okay, so now this time they don't want us to find. If I say to you guys, using this triangle, find sine of theta. Are you guys going to be able to find me what is sine of theta? I'm sure many of you can tell me what it is just by looking at the triangle. We know that sine, according to Sokatoa, is opposite over hypotenuse. So can you guys tell me, just by looking at the triangle, what is sine of theta? What is the ratio of sine of theta? What are we going to get? Be careful, Kulani. Yes, that's correct, Emmanuel. The opposite over the hypotenuse would give us 5 over 10. Right. The opposite side is over here, and this is the hypotenuse. Right. Opposite over hypotenuse. Easy enough. We can see that it's not even difficult for us to see at all. Right. Now, what happens when I say to you guys, find theta? Just theta. What am I actually asking for? When I say find theta, remember we said that things like theta and beta and alpha stand for the what? What am I asking for when I say find theta? Yes, absolutely. I'm asking for the angle. Find the angle. And now finding the angle isn't going to be the same thing as finding the ratio. Finding the ratio is easy. They're telling us what to use in order to find the ratio, right? When we have to find the angle, and I'm hoping you guys will help me make this trend. I've been trying to make it trend for 3 years now, and it's still not trending. I'm so mad. Okay, so whenever they ask us to find the angle, we are going to shift angle. See what I did there? Do you see what Teacher Coco did there? Whenever they say find the angle, we're going to shift angle. Huh? No? No? It's not working? Damn. Okay. I gotta make a trend, guys. Oh, come on, guys. Come on. Okay, we're going to use the inverse. Oh, I gotta make a trend somehow. I need to take it to TikTok. I think TikTok will do the things. Okay. So here's what we're going to do. All right. We're going to label this triangle. Step number 1 is always to what? What is step number 1, guys? Because you're laughing at me so hard. What is step number 1? Correct. Step number 1 is to label. So we're going to do exactly that. We're going to label. This is my adjacent side. This is my opposite side. And this is my hypotenuse side. Now, when we want to find the angle, let's say, for instance, we would use sine, right? We're going to go on our calculator. And now you've all shown me that we have those 3 letters. We've got sine, cos, and tan on our calculator. There we go. What you're going to do in order to find the angle, we're going to go theta is equal to, on your calculator, you're going to click shift. And then I want you to click the sine button. Click shift and click sine. And what your calculator is going to do is it's going to do this. It's going to go sine of -1, open bracket. That's what your calculator is going to do. Right. Now, inside, correct. It's called an arc function. Well done, Emmanuel. Good. Technically, it's not an inverse. It's called an arc function. So Emmanuel is like way ahead of you guys, because the inverse of a ratio is technically not a function, it is not an angle, but it is an arc function and it is the inverse in a way. Okay, so well done, Emmanuel. Good. So what we're going to do now, yes, a sweet for Emmanuel. Thank you, Narisha. A sweet for Emmanuel. Love it, love it. See, at least this catches on. Guys, we've got to make Shiftangle. We've got to make it trend, guys. Come on. Come on. Okay. All right. So what we're going to then do is we're going to click the fraction button. We're going to do that. Okay. We're going to click the fraction button. Now, if we click shift sign, okay, this thing isn't closed yet. It's not closed. Now, what we're going to do is, because we clicked sine, we know that sine is opposite over hypotenuse. Now, our opposite side is equal to 5. So we're going to replace the top part over here. Opposite is 5 over the hypotenuse, which is 10. So we're going to do that, 5 over 10. And then we're going to click to the right and we're going to close our bracket and we're going to click equals. Click equals. Tell me, what does your calculator give us? Absolutely. Yes, Narisha. Yes, Princess. It gives us 30. And what this tells us is that the angle theta is actually equal to 30 degrees. Do not forget the degrees. Angles are measured in degrees. That means this angle over here, theta, can actually be replaced with 30 degrees. Right. So thank you to the lovely Japanese architects at Casio for programming the whole of Hipparchus's big book into this tiny little calculator so that we don't have to walk around with a book. We can just click shift sine or shift cos and we will get the angle that is actually given to us. And Vukosi, are you seeing the difference there between the inverse and the ratio? Because you did ask a question about this earlier. I hope we're now seeing the difference. Okay, when we want the angle, then we look for the inverse or the arc. It is, Emmanuel, it is. Okay, it's coming. That section is coming. We're not quite there yet. Okay, it is very important that we know our special angles. All right, so we can do this exact same argument. We can do the same thing. We can say theta is equal to, now instead of clicking shift sine, we can click shift cos. We can click cos, and your calculator will do this. Cos -1, and it will open a bracket like that. We are going to click the fraction button. Now, remember, cos is adjacent over hypotenuse. Our adjacent in this case is 5√3. So at the top, we're going to click 5 square root 3. And at the bottom, we're going to put in 10. We're going to close our bracket and then click equals. Tell me what your calculator says. Absolutely, Theo, absolutely. Again, it's going to give us 30 degrees to prove that this angle and the ratios that we've been given on each side for this triangle are 100% equal, right? Seriously, I'm pretty sure we all know what's going to happen if we click shift tan, right? If we click shift tan and we use the exact same idea, tan TOA is opposite over adjacent, it's going to give us the exact same answer, guys. My opposite is 5 over the adjacent, which is 5 square root 5. And if we click equals, again, it's going to give us 30 degrees. To show you that for 30 degrees, these are the ratios we're going to get. If I did this, if I changed these angles, if I made this 10 and I made this 20 and I made this 10√3, What angle do we think am I going to get over here? What angle should we get? If we think of the way that Hipparchus has actually designed this, what angle should we get over there? If I've just increased everything by a factor of 2, what angle should I be able to get in that corner there? Not 60. Remember, it's a similar triangle, Tristan. Absolutely, Narisha. It's a similar triangle. The same thing. The ratios are going to be exactly the same. I'm going to get 30 degrees, even if I increase all the sides by a ratio of 10, of 20, or 2. If I increase all the ratios by a factor of 10, I'm going to get 30 degrees. If I increase all the ratios by a factor of 50, I'm going to get 30 degrees. Is it making sense, Tristan? Have you got me there? Are we okay there? Okay, so the angle will never change. The ratios for 30 degrees is always going to be the same. Absolutely, Emmanuel. The angle will always be the same. The ratio remains the same. The sides will increase, decrease, however they want, but the ratio will always be the same. How beautiful is maths, guys? Imagine that we can get the same answer for every single triangle as long as it has a 30-degree angle. It doesn't matter how big the triangle is. It doesn't matter how small the triangle is. Every single one of those triangles is going to give us the same answer. It'll give us some form of the same ratio. I think, guys, that's the most beautiful thing I've ever seen. I love trigonometry for this exact reason, because it makes sense. The math is mathing, guys. The math is mathing. All right, I'm going to take us through one more exercise. Let's talk about our game plan, guys. Okay, I know, right? W2 to the Pythagoreans and Hipparchus, they were really smart. All right, here's our game plan, guys. We're going to remember these things. Theta and beta and alpha all stand in place of what? What do all these things stand in place of? I know, Tristan, I know. Good, Emmanuel. All of these stand in place of any angle we want. They stand in place of angles. Excellent. Then, the first thing we always do when we see a triangle that incorporates theta, beta, alpha, step number 1 is always to what? Absolutely, Hilani, that's it, Princess. We are always going to label. That's our first step. And guys, I'm going to add in a couple more steps just to make this process a little bit easier. But I'm going to tell you now, you will not go wrong if you label. Things will become so much clearer if we label. Then from here, we need to remember the acronym WHAT. For sine, cos, and tan, what do we need to remember? In order for us to remember how sine and cos and tan go in a triangle, absolutely. Yes, that's it, Emmanuel. We need to remember so, ka, toa. Good. And if they ever ask us to find an angle, what do we click on our calculators? What do we click on our calculator if they ask us to find an angle? I told you, Emmanuel, I told you, I'm going to make a trend. We shift angle. I told you. We shift angle. Okay, whenever they want us to find an angle, we shift angle. See, guys, I told you. It's going to catch on. I swear. I'm going to make it a trend. I'm going to make it a trend. We shift angle. And guys, this is the game plan we're going to be following for the whole of trigonometry. And it's going to make our lives so much easier. All of this stuff that we're looking at over here, perfectly packaged for us to understand all the work that Hipparchus has put into it. Same thing, again and again and again. We're not going to change the rules in any way. They're going to be exactly the same again and again and again. All right. That's it. Thank you so much, ladies and gents, for joining me. This is where we're going to go. This is our introduction to trigonometry.